Welcome back, everybody. And in our next section for CCI Data Center in Nexus switching, we're going to be talking about the hardware architecture of the different platforms. And again, specifically within the scope of the CCI Data Center lab exam, we're mainly going to be dealing with four of these: the Nexus 7000, the Nexus 5000, the 2000, and the 1000V. Now, there are other additional Nexus platforms like the 3000 and the 4000 that are similar in operation from like a command line point of view, but since they're not within the scope of the lab exam, we're really not going to focus a lot on those, what their particular applications are. Then the last of these, the Nexus 1000V, again, we're going to be talking about the details of that within the scope of the computing class, because that's basically NXOS as a virtual machine that is running on top of the unified computing system, the Cisco UCS. So there's two main ways that you could get the hardware-specific information about this, and we are going to be referencing this periodically depending on the individual topics that we're talking about. But if you go to Cisco's website and go to cisco.com/go/Nexus, this is where you're going to find the data sheets about the specific hardware of what's the difference between 7K, 5K, what's the difference between the individual line cards. So if we were to click here on the, not the data sheets, the compare models, and this is going to give you a nice concise overview of what's the differences between the supervisors, what are the differences in the M series line cards versus the F series line cards. Also, what's the difference between the chassis, like the 7009, the 9 slot, the 7010, 10 slot, 7018, 18 slot. But another thing that we're going to show here specifically today is actually an iPad app that is the Cisco 3D catalog that allows you to basically look in detail at the individual line cards, the individual platform specifics that go along with the different hardware architectures. Now, for some of these, like the 5000 and the 2000, there's really not that much that we need to talk about with that, because like the 5548 that we're using is just a 1U fixed switch, and the same with like the 2232, which is a 1U fixed fabric extender. But with this, the 7000, Nexus 7K, there's a lot of different details that we need to talk about in its hardware architecture. So let's take a look here at the specific app, and this is a free app that you can download. Just go to the App Store and search for the Cisco 3D catalog, and it allows us to see in a little bit more detail exactly what's going on behind the scenes with these specific switches. So if we take a look at the switches here, and then go to the Nexus 7K, we see some of the particular chassis, which in this case are the 9, 10, and 18 slot variations.
This also, there is a 4-slot chassis as well. It's relatively new. It's not really covered even very much on the website. In fact, it was just announced at Cisco Live this year, but it's not in the iPad app. It's not really on the website yet, but it is a new option that exists. So if we take a look at, let's just say the 7009, which is specifically what is listed on the hardware blueprint for the lab, we just see an overview of the chassis itself. We see that it has a nice locking front where we can ensure that our cables go untouched, and we can go up to product animations up here, and we can choose to do various functions. We can open the door, and one of the reasons we're just covering this app is that we didn't want to take you inside a live data center and show you, deal with the sound issue and deal with our hardware and all the cabling, but actually be able to show you the hardware up front, just in case you don't happen to have the luxury of having this hardware in front of you. Maybe you'll be doing rack rentals from us later, but you want to kind of know what it is you're going to be working on. It's just nice to see. So we can take a look up here, and we can pinch to zoom in or scroll out. We can look at the various supervisors. They have different module slot positioning depending on the chassis. So we've got a supervisor 1 and 2 here in slot 1 and 2 on this particular 7009 chassis. Here in the middle, we have various fabric extender cards. I'm sorry, not fabric extender, fabric module cards. This is the crossbar fabric of the system. And then various line cards. We can pinch out, and we'll show some of these specifically. We can scroll around, and we can see the back plane of this. This is going to be slightly different than if we take a look at the 7010. which is actually what we have, and a much more common chassis. It's been around a little bit longer. The 7009 is a little bit newer. So we can open the doors, and this is actually what we're using in our data center. Functionally, in terms of what we're doing, the 7009, 18, and 7010 really have no difference in their functionality, except for the line card capacity. The 7004 does in the terms of its overall forwarding rate and the fact that it doesn't actually have fabric cards in it.
Yeah, so like Mark was saying, really the big difference between the chassis is just going to be the specifics of how many cards that it's going to hold, and also things like the power supplies, the fabric modules. Those are going to be a little bit different depending on what chassis you're working with. But from the supervisor modules and the line cards, they all do have the same support. So like here we see the back of the 7010 chassis where the fabric modules are basically like a full line card length that would plug into the back there. You can see specifically this platform can take up to 5 of them. Then we have pull the fabric module out. And this is kind of neat just to see, you know, the specifics about the individual cards. One implication of this that we need to talk about here also is some of the difference between the actual forwarding on the type of line cards in the data plane, like the difference between the M series modules and the F series modules. So basically, we have 2 different types of line cards on the 7000. We have the M series and the F series. M series is mainly for layer 3 forwarding. This is where we would have like our switch virtual interfaces. This is where we would be running OSPF. This is where we have things like OTV. And the key here is that they are feature-rich cards, so they don't run layer 3 line rate, where we were the flip side to this would be the F-series cards, which are the layer 2 only performance modules. Now, if we actually take a look, which particular card is this? This is the
M-series card.
The M2. So let's take a look at the specifics of the front of this, of one of the M cards. And what you would see, if we can we turn it to the side so we can get specific on the ports?
Yeah, let me do that in the.
Yeah, let's look at it into the 7009. You'll also see that the orientation is a little bit different from these. And there is actually another key point that from a practical implementation point of view you would need to think about is that they have different airflows. The 7010 has the airflow front to back, where the 7009 and 18 go side to side. So within your data center, like hot aisle, cold aisle design, that is a potential issue that you may need to think about. You know, which way is it intaking, which way is it exhausting, because they do generate a lot of heat, as you can imagine, in the data center. So we'll talk about the specifics of the individual cards that we have, but one thing that you'll be able to see from the front of the cards is this different notation of the ports. You can see a couple of these ports are yellow, and the other ones are just the normal like gray, white coloring here. And what this specifically means is the port groupings of the card. And we're going to come back to this and talk about it when we get to the virtual device context. But basically what this means is that in this specific card, which I believe is the 10 gig M1 card, which is actually, this is the line card that we're going to be using on the command line.
This is what's specified in the exam, the M132
right.
XP.
So for this specific card, you could see the 4 ports. The first one of them is yellow there. It means that that is the dedicated rate port of the port grouping.
So they basically all share an ASIC with these 4 ports, port 1, 3, 5, and 7. And we'll be talking a little bit more about these, as Brian said, in the VDC section. They all share a 10 gig ASIC, so they can't all have line rate 10 gig. In fact, if I want to make sure that one of them gets 10 gigabit Ethernet, then I have to, or I should, recommended, put it into dedicated mode. And dedicated mode, what that does is it essentially shuts off ports 3, 5, and 7. So these are odd contiguous groupings, or on the underside of the card, even contiguous groupings in the sense of 2, 4, 6, 8. And the dedicated port is the one that Brian was saying is yellow. And the reason for this, actually, if we pull the card out, makes a lot of sense from a hardware architecture standpoint, just in the sense of the way that the actual ASICs are positioned on the line card. So the top ports, we can see that there are on this animation, we can see that there's basically a daughter card on the very top of the blade, And then, of course, there's going to be ASICs on the bottom as well, if we could take a look at that. And so the ports that talk to the top daughter card are going to be using those, they're going to be using an ASIC that's attached to that top daughter card, so that's the reason why we have the odd contiguous. Okay, so we'll just go ahead and put that blade back in. And if we take a look at the, oh, sorry, there we go. So there we see the daughter card on the top, and we'll see like ports 1, 3, 5, and 7. Those would be on the top of the front panel. Those are talking to an ASIC that is on that top daughter card. I don't want to say daughter card in the sense that it's like another daughter card where we can add and remove it like a layer 3. It's not like that. I'm just saying it's not the main IC platform on the bottom. It's a riser card, I guess is a better way to say it.
Yeah, so you'll see when we get to the command line, it does get a little bit confusing about how the port groupings work and why you would need to do this to begin with. But when you actually physically look at the card, like Mark said, then it makes more sense. Because if we look at the front here, like the way that the ports are numbered, you would figure that port number 1 starts in the upper left, and then port number 2 is in the bottom left. So when you're counting the ports on the top, they're actually odd contiguous ports, 1, 3, 5, 7, 9, etc. And then likewise on the bottom left, we have 2, 4, 6, 8, and so forth. But the key here is that these restrictions are specific to the individual line cards. So not all cards have the same groupings. You would need to look at, is this an M card, is this an F card? And then also when we actually get into the VDCs, we'll see from the command line point of view, when we do the allocation of the individual ports, the command line is going to tell us what are the port groupings, and then how do we actually have to do this configuration-wise.
But again, on this that we're looking at so far, this is the M series. So this is the feature-rich layer 3, predominantly layer 3, can be layer 2 line cards. So next.
So the other thing we need to talk about then is what are the differences feature-wise between the M series and the F series. So if we take a look back at the slides here, some of the differences for the M series cards is mainly that they're designed to do layer 3 routing. But we'll also see that there's some other additional features that you can do on M and you cannot do on F. One of them we'll see today is for the fabric extender modules. So you'll also see this on Cisco's website when you go to the data sheet or the comparison about the different modules. Like if we were to go to M here, the particular card that we're using is the M132, which is a 32-port 10 gig layer 3 line card. And you'll see here that this one does support the fabric extenders, as well as the M2 cards, which are the second generation. Some of the other M1 cards do not. And then likewise in the F series modules, we basically have just 2 cards, which are the F1 32 1/10 gig E card.
And that is what's on the lab?
This is what we have, and this is what's within the hardware scope of the lab. So this is a dual rate. It's 1 gig or 10 gig. The M cards are, or specifically the one that we have is a 10 gig only card. But you'll see that this one does not support the fabric extender. The new F2 series card does, but the key point is that there's some very strange hardware specific limitations about how these cards work. Another one that is really big, key point here is the overlay transport virtualization, or OTV. So OTV only runs on the M series cards. If you were to have a chassis with F1 and F2 only, you would not be able to support that feature. The same with the TrustSec feature, which is going to be for like the link layer encryption with MACsec, and then also with the security tags. .1x, yeah. So things like that normal Catalyst iOS platform would support. And for the F series, likewise, we have other platform or line card specific features. Okay, mainly, as I mentioned, F series is going to be layer 2 only. F series is the only one that supports fabric path as well. So if we were to have an only M series chassis, then we're not going to be able to run the fabric path feature set. We'll also see, since fabric path has to do with the virtual port channel plus, or VPC plus, we would need to make sure that when we're dealing with the peer link, which is going to be for inter-process communication between the chassis that would have to be on an F-series port as opposed to an M-series port. So really, at the end of the day, these hardware-specific limitations do have an impact on the design and our configuration. Okay, another one that's key is that the F-series supports FCOE, Fiber Channel over Ethernet, and the M-series does not. But one thing that is really interesting here is that even though the F-series is a layer 2 only card, it can basically borrow the ASICs from the M-series card in order for the M-series to do proxy routing on behalf of it.
So if I had two different hosts in two separate VLANs that were both hanging off of a single F1 card, I couldn't do inter-process, I couldn't do inter-VLAN routing. So what I would have to do is that, and this link that Brian showed a little bit, we'll actually go to this here in just a moment, is a great white paper that really goes in depth on the architecture of routing it with classical Ethernet in the Nexus series environment from an F-series card. So if I want to go from a host on one to a host on another on an F-series card, I'm actually going to have to proxy route up through an M-series card. And the M-series cards are really the next generation Catalyst 6500 cards. Obviously, they're not the Cat 6500. They're the next gen cards of this, the Nexus 7000 being the next generation switch. The F-series cards are really a brand new architecture altogether. And if you even saw on the iPad app that we had here, we had this, we could see the individual, what are called switch-on chips. So the individual ASICs or application-specific ICs, Cisco calls them switch-on-chip or system-on-chip. They sometimes refer to them both ways, or the industry sometimes refers to it on system-on-chip. This is basically the entire architecture of the switch boiled down into the ASIC, and you can see these huge heat sinks. I mean, they're really large heat sinks. So I think on this particular card we have 16 ASICs, and I think that even on a 32-port card we have 16 ASICs, and that really determines the port grouping. So if it's a 48-port card, then we're going to have obviously more ports to a particular ASIC. A 32-port card, we're going to have 2 ports to a given ASIC. But what this really allows is an extremely high performance layer 2 only throughput. And that's the idea, is that the F-series card was designed for extremely high performance, but not all of the features that, if it needs, it borrows those proxy functions from or proxies through the M-series cards.
So this specific link here, this is part of the Cisco Design Series. So if we take a look at this on Cisco's website, so it's Design Considerations for Classical Ethernet Integration of the Nexus M1 and F1 modules. So I would definitely recommend to bookmark this and to take a look at this afterwards. But one of the things that I wanted to show here quickly is just a visual view of what they talk about happens behind the scenes when traffic is actually routed through the platform, which is right here. So it says, if the chassis is using both M and F series cards, then basically the F series cards is going to borrow the layer 3 features from the M series. So depending on what the source and the destination of the traffic is, so if we look at this graphic on the upper left here, it says a packet came in on an F1 module in VLAN 10, and it was trying to go to VLAN 20 on an additional F1 module. So it has to go internally to the M1 ASIC first and then bounce back, which technically is 2 passes through the fabric, because it's kind of like a router on a stick internally to the platform. So this is kind of a design consideration that you need to think about when you're placing your services in the data center, figuring out which particular cards are they going to connect to. So do I really need layer 3 features for this specific connection, or can I get away with layer 2 only? Because it is going to impact like the overall forwarding and the throughput depending on which particular cards that we're using. So beyond this, we're not going to get too much more into the specific hardware architecture. You'll see there's tons of design documents that are on Cisco's website. So I would recommend to take a look at that.
Mainly because I don't see too many possibilities of them even being able to test this in the lab. This isn't CCIE focused implementation stuff. It's more design focused. So if there ever became a CCDE data center, then that would be
definitely this would be applicable. Yeah,
part of what you would need to know. But it's certainly good to know for the real data center implementation.
Yeah.
Absolutely
So for practical
critical.
implementation, you would want to definitely take a look at this, which again is classical Ethernet integration of the F1 and M1 modules. Okay, we'll talk about this a little bit later. What does that mean, classical Ethernet? With the introduction of the new Fabric Path feature set, they're basically saying that normal Ethernet is now legacy or classical Ethernet, and now Fabric Path is the next gen of forwarding. But anytime they're talking about classical Ethernet or CE, they're talking about just regular layer 2 switching, like you would see on your 6500 or your access layer switches like 2960. Okay, the next platform we have then is the 5000. Nexus 5000 is mainly going to come in two different generations. There's the Nexus 5000 and then there's the Nexus 5500. The main difference between these is that they're both mainly layer 2 switching. So they're mainly going to be for like aggregation of your access level ports, where sometimes this is called the end of the row, or EOR, which basically means like from my end servers or virtual machines, I have bunches of cables coming off from them, and then going to some sort of top of rack aggregation switch, like a fabric extender. Then the cables are going to run from the top of the rack down to the end of the row, which is where the 5K is going to sit. So most of the time, this is going to be like our, not necessarily the access layer. It gets a little fuzzy when we try to apply the traditional design logic of three-tiered Ethernet, like access, distribution, and core, onto the data center, because the lines are kind of blended together, and we'll see that when we look at the specific implementation of how some of this stuff works.
And nobody ever said that you have to do, well, Cisco said you have to do it that way, but that doesn't mean that you actually have to have a core distribution or aggregation, if you want to call it that, and access level.
So mainly the idea of this is that your 5K is going to be like your access switch. So it's going to be doing your layer 2 switching, and then any layer 3 functions, you're going to forward it up to 7K, and that's going to have to talk to the M1 ports. You technically can do layer 3 switching here. There's an add-in card for it that's supported on either the 5548 or the 5596, where the 5548 is a 1U platform, 5596 is the 2U version, but basically the same functionality between the two of them. So if we look back here at the animations here, this is I believe this is the 5010.
This is the 5010, yeah. The actual iPad app doesn't have the newer 5500 series, but it doesn't look very much different at all, save the add-in module that you can do over to the right. One of the differences, one of the major differences, I don't know if you already covered this, but the fact that we can, with a older 50 series, we can actually implement or insert over here a fiber channel module. And with the new 5500 series, we're going to talk about, I think, two different variations of this, the standard 5500 and then the 5500 unified port, where we can make any port in either Ethernet or fiber channel.
Right. Like Mark was saying, there's of the 5500, then there's two sub-models of this: the regular version and the UP. Specifically, the ones that we're going to be demoing this week are the 5548 UP models, which basically means that any of the ports can run either as Ethernet or as fiber channel. Now, there are some caveats with this, and this is kind of important to note. We're going to obviously talk about this more in detail when we get to storage, but when you're provisioning the switch, your regular Ethernet ports start at the first port and count up, where the native fiber channel ports start at the end and then count down. And the reason that's significant to note is that if you want to change the port's role, you have to reboot the switch. So it's kind of like how some of the lower level access switches have the switch database manager that's changing like the allocation of the buffers behind the scenes, and it requires a reboot in order to actually apply that. So similar type concept here, where we're reallocating what is going on with the individual ASIC of the port, because obviously Ethernet and fiber channel are not the same frame format when we're dealing with a layer 1 and layer 2 format. So you need to take that into account for your design, that if you're changing it or adding more fiber channel ports, that you would have to schedule this in a maintenance window because you're going to have to reboot the platform. But again, we'll talk about this in more detail when we get to the actual storage class and look at the differences between running native fiber channel, running fiber channel over Ethernet, and then other options like fiber channel over IP or iSCSI, and then how those fit into the overall design. Okay, the last of these then we have is the Nexus 2000, the 2K, or the Fabric Extender, or FEX, where basically what the FEX is just a remote line card, where it can either be combined with either the 7K or the 5K chassis, where those are considered the parent switches of them. And one of the key features to note here in the design is that the 2K does not support local switching. So what this means is that if you were to have two end hosts that are on the same VLAN connected to the 2K, you would not be able to send traffic directly between them without first going up to the parent switch and then having the traffic come back down. So in the case that the 2K is used for your top-of-rack aggregation, this does play into your design. Let's say you have two different virtual machines that are on different physical hosts, where one has one physical 10 gig NIC card, another one has another physical 10 gig NIC card. If you want them to constantly talk to each other, it means they would have to go all the way down to the end of the row, and then the traffic returned back to the Fabric Extender before it could go down to the final host. So we'll see beyond the design, there's really not that much configuration issues that go along with the 2K. We are going to take a look at that today on the command line. How do we marry the 2K with the 5K as its parent, and then how do we have it as using the 7K as its parent? And it's going to be one or the other at a time. So you cannot have the 7K and the 5K both at the same time talking to the same FEX. The main reason why is that they're running different software versions, where the 7K, we have it running a 6.0 revision, and then we have the 5K running a, I believe, 5.1. So they're not going to be able to both talk to the chassis at the same time. But there's definitely some interesting topologies that you could run into when we're dealing with the Fabric Extender. We'll talk about that today, whether we're doing static pinning or whether we're doing virtual port channels. It kind of goes against all previous designs that we had in like classical enterprise LAN campus design that is specific to data centers. So definitely an important topic that we need to talk about here. Now again, as we're going more through these specific topics and actually implementing them, looking at things like how do we configure OTV, how do we configure Fabric Path, how do we configure VPC+, we're going to be returning to the specifics of the hardware platforms, because there are a lot of caveats that go along with, you know, based on this version, based on this line card, based on this supervisor, based on this chassis, can I actually support this feature in this design? So it is definitely important to know what you can or cannot do in order to solve your particular problem. Now, like Mark said, within the scope of the CCI lab exam, since it's not a design test per se, there's really not too many ways that they could test you on that. But still, from a fundamental knowledge point of view, you want to understand how all of this stuff works. That when you actually go to implement 7K or 5K in your data center, that you know what are some of the limitations, that I don't want to get all the way, build my bill of materials, go through all purchasing, you plug the platforms in, then you realize you can't even do what your original design was trying to accomplish. So again, we will revisit these as we get into the more specific details of the actual implementations. Okay, any additional questions up to this point on the hardware-specific topics of the lab exam? A couple questions. Are we going to be going over the SUK 2E, M2, and F2 components? If you take a look at the hardware release notes again on the website, really this is where you want to check for any of that specific information, because mainly what it's going to tell you are things like what is the version that's required in order to run. Then, like here, we could see for the F2 cards, you cannot run OTV with them. You cannot run Lisp or MPLS. So that's going to affect your design.
The F2 card adds layer 3 support. So the reason that we probably won't be covering that too much is that we don't have that card in our chassis, and the reason we don't is that it's not specifically listed on the CCIE data center hardware architecture. So since it's not on that, this class is really going to focus on the hardware and software versions that are tested in the lab. There may be newer software versions that can and will come out even as this class is recorded and goes on, that can accomplish more. And as the CCIE Data Center Lab grows up, evolves over years, and possibly changes blueprint, we'll certainly incorporate that. But as for right now, we're focusing on what is in the lab for right now.
And that's actually a really important point to mention here. There's a lot of hardware caveats that are software specific on the platforms. Now, what I mean by this is that there's going to be features we see will be supported on 7K but not 5K, because of course there's a different hardware architecture, but there's also a specific software version. So you may see that some of the topics that we're talking about are only in reference to the individual versions that are within the scope of the lab exam. So for example, if you were to use F2 cards and have the latest revision, there's going to be some designs that you can't accomplish that we're not necessarily going to talk about, because those wouldn't be the designs that you would face in the actual exam. So it's kind of like a disclaimer before we get into any of these topics. Is you'll see everything is very, very hardware specific, very, very version specific to these individual platforms. And also one thing that you're going to want to do, if we take a look back at the documentation real quick, and let's go to the 7K documentation, you'll see that there are some of these documents that are the configuration limitations, and they may be under, it depends on the particular platform we're looking at. Let's say 5K configurations. So here it says there's different limitations if you're running 521 versus limitations that you have if you are running 513. So you may want to take a look at these specific hardware and software release notes to figure out what is supported, what is not supported in that particular release that you're going to be dealing with. But really at the end of the day, when you want to get the hardware specific information, you do need to take a look at these hardware release notes in more detail, which is going to be the stuff here in the comparison sheets. And then when you actually go to the data sheets for the modules, that's going to tell you what are the specific features that are or are not supported on those individual cards.
So someone was asking if we created a layer 3 port on an F-series card. Actually, if we did not have an M-series card in the chassis at all, could we still inter VLAN route through the CPU? And the idea, the architecture of this box is if we need to have layer 3 routing, we want to have an M-series card in here. We don't want to be passing any traffic through the supervisor CPU. It's not designed as a data plane. It's really designed as a control plane mechanism that then writes those switching forwarding tables down to the distributed. That's the whole idea behind switch on chip, is that each of these ASICs really is a complete switch architecture, well, in so much that that particular ASIC supports, and that's what you just got done discussing, is that different ASICs, different hardware cards are going to support different features. But as to whatever features those ASICs support, the supervisor then writes that information down to the feature card, down to the ASIC level, and that switch on chip, that individual ASIC, performs the forwarding features for those ports, possibly passing them off to other individual ports on the same line card, doing local switching. There's actually 3 fabrics in the system. Someone asked a question about fabric. We're going to talk a lot more about that when we talk about QoS. But there's really, just as a brief primer, there's 3 basic fabrics, or 3 different types of fabrics in the system. There's going to be the fabric that is on the individual line card. We saw those line cards being pulled out through the iPad animation. There's going to be a fabric that's there. It can do local switching. Now, we are not talking about the FEX. That cannot do local switching. The fabric extender, or FEX, same thing. But we're talking about the 7000 series, the line cards. Those can do local switching, and they have their own fabric to be able to, or really, fabric is a fancy word. Basically, it's traces on the mother. Physical traces, right. And then a central arbitrator that handles all the decisions for inter-ASIC or inter-switch-on-chip forwarding. I don't want to say routing, because it could be, and a lot of times is, layer 2 forwarding. So that's the whole idea of this. We've got that individual fabric on the individual line card. on the ingress, and then we've got the fabric on the egress line card, assuming it's a different line card that we're going out of. And then we have to marry those two together through the crossbar fabric of the system. So basically through the fabric or the switching architecture that is central, that ties those individual line cards together. That's what those fabric cards are there for. Now, I mentioned that the 7004 doesn't have that fabric. It doesn't have the individual line cards. It's just built into the individual supervisor engines. That's really a limited use case device. The 5000 series, that's going to have that central fabric or system fabric built into the backplane, built into the motherboard. But for the 7000 series distributed, for the 7009, 10, and 18 series chassis, that's what those individual fabric cards are there for. And the more fabric cards we add, the more switching capacity we add to the system. Each of them,
the backplane of the switch is what the fabric
we're increasing the backplane capacity of the switch, exactly correct.
Answering to this point again, can you actually create a layer 3 port on the F-series card? We are going to get into this specifically today when we take a look at the command line. But the F-series port itself generally is going to run in 3 possible modes. And we'll see there are some exceptions, of course, to any rule. It's generally either going to be a layer 2 access port, it's going to be a layer 2 trunk port, or it's going to be a layer 2 fabric path port. This means that you cannot put the port into no switch port mode, which would make it a native layer 3 routed interface.
At least not the F1.
On the F1, correct. What you would have to do is create an SVI, an interface VLAN, that is basically borrowing the ASIC from the M1 card in order to allow you to route between the F-series ports. But going along with this, another important point to note is that since it is using the processing power of the M1 cards, if you were to have a chassis that is all F cards and only one M card, if that M card goes down, you lose layer 3 forwarding on all of the F ports. So based on the distributed architecture, and we'll talk about this a little bit more today as we talk about things like the power redundancies, supervisor redundancy, the high availability policy, really is kind of a minimum implementation. You would want to have your 7K with 2 supervisors, with 2 M1 cards, and with 2 F1 cards, or F-series, F1, F2, M1, M2. But then again, you even get into more specifics about where can the F2 exist versus the other ports.
And it sounds like we're all of a sudden system account managers from Cisco or sales engineers. And the truth is there's a reason for adding the distributed architecture. If we talk about data centers, we're not just talking about a branch office router, but if we talk about core data centers and mission critical data, we really can't have this, we can't have these paths go down. We can't have these layer 2 or layer 3 paths go down. And so adding in all of this redundancy, while it may seem unnecessary if you're not familiar with data center architecture builds, there is really good reason for all this stuff. And we're going to be going into some of the specific reasons that would pertain to the CCIE lab in terms of redundancy, especially when we get to things like VPC. But we'll be talking about those as we come to those topics.
Our next section, we're going to jump on the command line. We're going to go through our first section of the basic initialization of the platform, go through some of the initial management techniques, talk about things like the Cisco Fabric services over Ethernet, over IP, how that's going to be used and required for some features that later we're going to be building on top of it, things like VPC or lots of other topics that we're going to be talking about that are more specific to data center.